Okay, so at the end of last lecture, we started to talk about uh, energy involved in chemistry. And we discussed that energy are generally, energy we discuss here can be generally put into two different categories. There's kinetic energy and there's potential energy. Kinetic energy is the energy of motion. Potential energy is stored energy, and heat is a form of kinetic energy. Now, and since we're talking about heat, what is the heat that we discuss here? We use lowercase letter q to represent it. Okay, when we study heat, we are actually studying the change of heat content. Okay, so generally speaking, heat is a state function, which means that you can only study the change of it. Now, what do you mean? Well, you can't say, you can't point to an object and say, well, this thing contains how much heat. Okay, the only thing you can do is, okay, to compare this particular thing at different stage, different temperature in the situation of heat. Now, from a lower temperature to a higher temperature, how much difference, how in energy, now this thing is gaining or losing. Okay, so now, so when we study heat, an important index is the change of temperature. Change of temperature obviously is final temperature minus initial temperature. Okay, and when something's temperature delta T increase, so when your temperature delta T is positive, okay, that means your temperature is increasing. And temperature increasing means that you're going to have a positive amount of heat. Yeah. So absorb heat or absorb energy. Okay, if your temperature change for the object is negative, that means your temperature is decreasing, and that means your Q is going to be negative, and that means your object is losing heat or losing energy. Yeah. And if you're going to measure how much heat is involved, you're going to have a unit for the heat. Okay, and because heat is a form of energy, the unit of heat is also the unit of energy. The international standard unit for energy is joule. We use capital letter J to represent it. Okay, the English unit for heat is calorie, CAL. No. And when we're talking about a calorie, I want you to differentiate, like kind of a real life knowledge nugget here is that you always look at if you look at food packaging, okay, you see for certain food how it on the packaging it labels how much heat it is contained in the food, okay, and calorie is a very common word, a very common unit people use there, but that calorie is not this calorie. If you look at it, you see this, or you see capital CAL. One food calorie, okay, is actually 1,000 of the lowercase calorie that we're talking about here. Okay, and between the two units, one lowercase calorie is about 4.184 joules. Okay, so how did you define calorie? Why do you have this weird number of 4.184? 1 calorie, lowercase c, is defined as the amount of heat needed to raise the temperature of 1 gram of water, liquid, by 1 degree Celsius. Okay, 1 gram of water is about 1 centimeter cube or 1 milliliter. So to make the temperature of that 1 milliliter of water to change by 1 degree Celsius, whether if it's going up 1 degree Celsius, you're going to need to absorb 1 calorie of heat. And if it's going down 1 degree Celsius, you're going to have to release 1 calorie of heat to the environment. Okay, and now, how do we relate temperature and heat? We know temperature is an index to show you, okay, change of temperature is related to amount of heat absorbed or released, okay? But to be able to do that calculation, we have 3 different thermal properties we're going to discuss here. The first one is called heat capacity. Heat capacity, we use capital letter C to represent it. This is the amount of heat needed to raise the temperature of an object by 1 degree Celsius. And the unit of it is either joules per degree Celsius or calorie per degree Celsius. And notice that heat capacity is about an object. Okay? And what do you mean? Now, 1 cup of water could be viewed as an object, and 1 full bathtub of water can also be viewed as an object. Okay? The entire Chile Lake's water body can also be viewed as an object. Okay? And obviously, you can see, okay, it takes different amount of energy to change the temperature of those 3 objects by 1 degree Celsius. A cup of water, you probably don't need much heat to get the temperature up. An entire bathtub of water, you probably need substantial amount of energy to get the temperature to go up by 1 degree Celsius. You know, the entire Chile Lake, okay, you're going to need a tremendous amount of energy to change its temperature. So, in this case, for this particular property, heat capacity, size matters. If size matters, what type of energy is heat capacity? Heat capacity is a extensive property. Okay. Thermal property number 2 is called specific heat capacity, or in short, people also call it specific heat Same thing. Okay. Now, and we use capital letter C sub P to represent it. Now, the definition is actually very similar to heat capacity. This is the amount of heat needed to raise temperature of 1 gram of a substance by 1 degree Celsius. So with the same thing involved, you can see that this is going to have a different unit. It's joules per gram per degree Celsius, or calorie per gram per degree Celsius. Okay, now what's the difference? This is specifically 1 grams of a substance. So using the example that we used earlier, you view a cup of water, a bathtub of water, and the entire chi lake of water, okay, as 3 different objects. But what's in those 3 objects? Just water, okay? And when it comes to specific heat, okay, it's 1 gram of that water. So that cup of water, that bathtub of water, the entire chi lake water body, okay, if you want to talk about specific heat capacity, you have to take just 1 gram of water out of those 3 things. And since all of them have just water in it, we're going to ignore that bathtub chi lake water has, some kind of impurity in it. Don't worry about it. Just fresh water, okay? 1 gram would have the exact same heat capacity, specific heat capacity. It would just need the exact same amount of energy to raise 1 gram of that water by 1 degree Celsius. So for specific heat capacity, size doesn't matter because we have already limited the size. Okay? Yeah. It's like density. Okay? Yeah. If you have a small nail, iron nail, or you have a huge iron dumbbell, okay, the density is the same density of iron. Size really don't matter for density. And same thing here, specific heat, size really doesn't matter. And if size doesn't matter, specific heat is obviously a intensive property. Okay, and the third thermal property we could be using in this part of Chem 115 material is called molar heat capacity. We use capital C sub M to represent it. This is the amount of heat needed, and you guessed right, to raise the temperature of 1 mole of a substance by 1 degree Celsius. Unit is joules per mole per degree Celsius, or calorie per mole per degree Celsius. And the only difference it has with specific heat is that you change the 1 gram of stuff into 1 mole of stuff. And since you are also limiting the amount of the substance, for molar heat capacity, same deal with specific heat. Size don't matter. intensive property. Okay, now for these three different thermal properties, the calculation for amount of heat involved, depending on which one of the three thermal properties you're provided, we have three different equations. The, okay, amount of heat involved in a process Q, okay, should equal to C times delta T, okay, if you are given heat capacity. Q also equal to mCp delta T. This is specific heat, and for specific heat, you would need the mass of your object to calculate the amount of heat needed or released. And if you're given molar heat capacity, if we use number of moles, use N to represent number of moles, that Q equation should be N C sub M delta T. Okay, so if you think about the units involved, C has joules per degree Celsius or calorie per degree Celsius multiplied by delta T, which have degree Celsius, you're going to end up with joule. Now, CP has joules gram degree Celsius. You multiply by mass, which is gram. You multiply by delta T, which is degree Celsius. You can see both grams and degree Celsius cancel. You also ended up with joule. And then, of course, for the molar heat capacity, joules per mole per degree Celsius, number of moles, have the unit of mole, and delta T has degree Celsius, so mole cancel. So you can see you also end up getting joules or calorie as the unit for your Q, which is what we defined earlier. All right, so with these three different equations, okay, now, depending on what conditions are provided or what is the question asking, you're going to choose different ones to do your calculation. So take a look at this simple, very simple example here. 125 grams of 48.0 degrees Celsius water absorbed 500 calorie of heat, and its temperature rise to, oh, not 48, 52.0 degrees Celsius. Calculate C, Cm, and Cp of the water involved in here. Okay, so C obviously should equal to Q over delta T. So 500 calorie divided by 52.0 minus 48.0 degrees Celsius, and you ended up getting 125 calorie per degree Celsius. Specific heat Q over M delta T. Just simply rearrange the equation. 500 calorie over 125 grams times 52.0 minus 48.0 degrees Celsius. Okay, so you ended up getting 1.0 calorie per gram per degree Celsius. Okay, and then if you want to CMQ over N delta T, 500 calorie divide by 125 grams times 18.02 grams of water, 1 mole, and then multiply by 4.0 degrees Celsius, which is 52 minus 52.0 minus 48.0. Okay, and the calculation gave me 18 calorie per mole per degree Celsius. So depending on what the question is asking, what the question is providing, you use different equations to do your calculation. And once you know what conditions you have, this is simply a rearrangement of the equation and then punching number into calculator. So easy stuff. One more example. How much heat is involved when a coin with a heat capacity C equal to 2.00 joules per degree Celsius change its temperature from 22.5 degrees Celsius to 22.0 degrees Celsius. So we have C, so Q equal to, we want heat, so C delta T, 2.00 joules per degree Celsius. Final temperature is 22.0 minus 22.5 degrees Celsius. Cancel. And the calculation gave you -1 joule. Now, I'm not giving you this example for you to worry too much about the calculation here. You can see, okay, the calculation involved two numbers, okay, C and delta T, both of which are either provided or very easy to calculate. Now, the whole point of this question here, I want you to be familiar with negative Q. Okay, whenever you have the heat, okay, being a negative value, okay, I want you to view it. I don't want you to view it as, oh, I created negative energy. Okay, no, that's not how it is. Instead, I want you to think it this way. Okay, negative Q simply means my object, in this case the coin, losing heat. Okay, your temperature went from a higher temperature to a lower temperature. Okay, your thing is cooling down, and as you cool down the object, okay, well, where did the energy go? The energy is released to the environment. So negative Q simply means object or substance losing energy, losing heat. All right, so now, so far this is all conceptual stuff, and the calculation involved are very straightforward. Simple algebra rearrangement can get us to the right answer. But all of these situations happens with one object. Okay, it's temperature going up, temperature going down. and you use one of the equations and you do your calculation. But what if we don't just have one object? Okay. What if we have two or even more different things, okay, transferring energy between them? Yeah. What if I have multiple object situation? How do we deal with heat? Okay, before we do that, let's introduce a concept that's called insulated system. Or you could also see it being called isolated system. No difference. Okay, yeah. All right. Insulated, not insulted. Yeah. Sorry. No. All right. So, what is an insulated system? Well, you've all heard about the word insulation before, okay? As long as you lived in houses, okay, you've seen drywalls right behind it, okay? It's those insulation material that people put in. Why do we put insulation in the drywall when we build a house? Oh, well, to keep the temperature inside the house, like you have an AC in summer, you lower the temperature inside the house. You don't want, okay, the outside heat coming in too easily. Okay, so having insulation blocking the heat out in summer, and in the winter when it's cold outside, and you're heating up your house, you don't want the heat that you created and you spend money on, okay, to go to the outside cold environment too easily. So that insulation also blocks your heat from releasing to the environment. And for insulated system, the word is the same deal. Okay, an insulated system is a system that cannot exchange matter or energy with its surroundings. Okay, now, what do you mean, and what good does this do? Now, the whole point of an insulated system or isolated system is to simplify our heat transfer process between a cold object and a hot object. Okay, we don't want to deal with situations that's too complicated at this level. So we're going to try to simplify things into a model. What do you mean? Well, think about when you put a hot object together with a cold object. Okay, what's going to happen when you put a hot thing and a cold thing together? Okay, imagine in the morning you prepared your coffee. Okay, you put some hot coffee into your coffee mug. Okay, the coffee that is something that you just prepared the coffee. Okay, boiling hot. Okay, the cup has been on the table. The mug has been on the table for a while. Okay, so it has room temperature. So obviously the two, coffee and the cup, the mug, have a temperature difference. Okay, and when you have temperature difference, you're always going to have heat transfer. Okay, so inside the mug, okay, wherever the mug and the coffee got in touch, hot coffee's heat is going to the cold mug, and it's going to increase the temperature of your mug, okay? And then eventually, okay, the two is going to end up at the same temperature. Yeah. But what makes this situation more complicated in real life is that, well, you have air surrounding your two objects, okay? You have air above the surface of your coffee in the coffee mug, okay? So energy could also go transfer to the air from your hot object. An evidence is that, okay, once you pour that boiling hot coffee into your coffee mug, okay, you don't need to touch the coffee to know that it's hot, or you can touch the coffee mug and you can feel the coffee mug warming up. That's heat transfer. Okay, you can put your hand right on top of the coffee surface above the mug. Okay, if you put your hand close enough, you're gonna feel, okay, the air in that area is getting warmed up by the coffee. So, and of course, to make the situation even more complicated and realistic, well, where is your mug? If your mug is on the counter, well, what do you think is going to happen when your coffee mug is heated up by the coffee? Now it's going to start to transfer from the mug to the counter. Okay, and pretty sure, okay, when you remove that coffee mug and if you let it sit there, the hot coffee sit there for a while, you remove that coffee mug and you touch that portion of the countertop where the coffee mug was, you're gonna feel, okay, the temperature of the counter actually increase. So that means there's also energy transferred into the countertop, okay? And that makes the situation much more complicated and with way more things involved, okay? How am I going to end up doing this calculation if I want to find out, if I know what kind of temperature they have, I know what kind of thermal properties they have, okay? I need to calculate, okay, what is the final temperature, the same temperature between the coffee mug and the coffee. If we consider coffee is also losing heat to the environment, coffee is to the air, and the coffee mug is losing heat to the countertop, then you can see how complicated that calculation is going to be, okay? And that's where, if we want to simplify the situation, we say, well, I can just put those two objects, the coffee, the hot, and the mug, the cold. Can we imagine that they're in a box? Okay. Let's forget about air. Let's forget about the countertop. Let's focus on the two main things. And once you put that box of insulated system on it, okay, you can say, well, heat is not going out of the box. Okay, there's no air in the box, so you're not going to waste energy on heating up the air. Okay, there's no countertop, so you don't have to waste energy to heat up part of your countertop. Okay, and now you can simply just consider the two objects. Okay, so heat transfer from hot object to cold object, and no losing. Okay, and also it's preventing outside energy from getting onto your hot or cold object. And that's what insulated systems do. Okay. Now, once you establish the insulated system like this, an equation can be very easily set up. And this is the format of that equation. We call it Q lost and Q gain. Now, you only need to consider these two objects, the hot object and the cold object. Okay, so for the hot object, it's going to lose heat. For the cold object, it's going to gain heat. Okay, and because energy is conserved, okay, whatever heat your hot object is losing, where does it go? Don't worry about air, don't worry about the countertop. We use the insulated system to block them out. And then you can say, well, all the heat, all the Q, the hot object lose, it must have gone to the cold object. Okay? And you can see it from, also look at it from the cold object's angle. It's gaining some heat. Okay, every bit of heat it's gaining is not from the air, it's not from the countertop, it's strictly coming from the hot object. Okay, and we just said that if you're absorbing heat, it's positive. Okay, for cold object, it's positive. Now, for the hot object, okay, you're losing heat, so it's negative. Well, what if I put the positive number and negative number amount of heat together? Well, whatever amount of heat, okay, because energy is conserved, let's emphasize that. Now, whatever amount of energy the hot object loses should completely go to the cold object. Okay, so the hot object has a negative Q value, and the cold object would have a positive Q value. And put them together, because energy is conserved, you get this big zero. Okay? Within an insulated system, within an insulated system, heat gain and heat loss of all objects, okay, should add up to 0. Okay, however much heat you lost is from one or multiple object in the system is going to, okay, completely transfer, okay, into one or multiple cold objects. And now, in a way, for insulated system, you can view it as Vegas. Now, we all know that saying about Vegas. Okay, what happens in Vegas stays in Vegas. What happens in your insulated system stays in the insulated system. Nothing goes out, nothing goes in. And now, once you have established the insulated system concept, okay, now we can do some deal with some more complicated heat transfer situations that involve multiple objects. Okay, so here's our example. A quarter at 37.0 degrees Celsius is dropped into the glass of 28 grams of beer at 2.0 degrees Celsius. If the quarter has heat capacity C, that's 1.7, okay, calorie per degree Celsius, and the beer has heat capacity of 1.0 calorie per gram per degree Celsius. What is the final temperature in the glass? Assume the glass itself did not absorb or release any heat. Okay, so now, long question, okay, worthy too. Yeah. Multiple numerical conditions, okay, and how do we analyze this problem? What do we do? Where do we start? Okay, so let's think about the scenario. You have a quarter, and let's say this quarter is in your pocket. It has your body temperature of 37.0 degrees Celsius. Okay, and somehow it got dropped, it bounced around, and eventually into this glass of leftover only 28 grams, okay, of beer, and the beer obviously is pretty cold at 2.0 degrees Celsius. Now, if we know the thermal property of the quarter, the coin, and the specific heat or another thermal property of the beer, now we want to know eventually, now, what is the final temperature within that glass. Now what's going to happen when you have a hot quarter dropped into a cold beer? Well, you have two objects, one hot, one cold, got in touch with each other. Okay, now, obviously, your quarter is going to lose heat, okay, and your beer is going to start to absorb whatever heat that the quarter is releasing. So the process starts with your quarter temperature start to go down, your beer temperature start to go up. Okay. How long does that process last? No, I'm not asking you a specific time. Okay, I want you to think, okay, one of them is temperature going up. So for the beer, it's at 2.0 degrees Celsius, that temperature is going to rise. Okay, and then you also have the quarter at 37.0 degrees Celsius. Okay, its temperature was going down. Okay, now eventually they're going to meet somewhere. Okay, they can't go up or go down forever. Okay, they're going to meet somewhere in the middle. And the moment that these two temperatures meet each other, okay, which means they're having the same value, okay, then do you still have heat transfer? No. Your beer and your quarter are at the same temperature now. Okay, now, and because we're assuming the glass didn't do anything, there's no heat transfer, we're putting this into an insulated system. Okay, now, so supposedly at that point, both of the two objects, the beer and the quarter, okay, stay at the same temperature happily ever after. Now, and we want to know, what is the temperature? What is this temperature at that particular moment? All right, so now where do we start? Well, for any insulated system, okay, how do I know this is the insulated system problem? You have a system, you have heat transfer between two or more objects. Okay, all of those are insulated system problem, because without insulated system, there's too many uncertainties. Okay, how do we assume this quarter lose heat to the air? How do we see the beer, okay, cooling, absorbing heat from the environment or releasing heat to the environment? Now, if you have all these uncertainties, then we can't do this calculation. So this has to be within a insulated system. And if it's within insulated system, the starting point is always easy. Q lost plus Q gain equal to 0. Okay? Now, who's losing heat? This obviously is the quarter. Okay? And this obviously is the beer. Yeah. Well, how do we calculate the Q of the quarter? Well, what do we know about the quarter? We have a C here, so Q of the quarter, Q lost. Okay, the amount of the heat lost by the quarter during this process is C delta T of the quarter. Okay, and what about the beer? The beer, we are provided with a different thermal property, Cp, so M of the beer times Cp times delta T of the beer. That should equal 0. Okay, now let's start to plug stuff in. C is 1.7 calorie per degree Celsius. Delta T is final temperature minus initial temperature. What's the initial temperature of the quarter? So final temperature minus 37.0 degrees Celsius. Okay. So degrees Celsius cancel. I get a calorie for the quarter, and then MCP delta T 28 grams of beer. 1.0 calorie per gram per degree Celsius. Grams cancel. And delta T of the beer is final temperature minus initial temperature of the beer, 2.0 degrees Celsius. And then, of course, degrees Celsius cancel. And you have calorie. These two things together equal to 0. Now, All right, so rearrange your equation. So 1.7 times t minus 37 plus 28 times 1.0, that's still 28. T minus 2.0, okay, and that equal to 0. Rearrange your equation, so 1.7 t minus 1.7 times 37.0 plus 28t times minus 56. That equals 0. Rearrange your equation, so 1.7 plus 28 t should equal to 1.7 times 37.0 plus 56. All right, so calculation show me and follow your sig figs. Delta t, t final, not delta t. Should equal to 4.0 degrees Celsius. Okay, so with the quarter lowering its temperature and the beer raising its temperature, the two of them, those two temperatures will meet at 4 degrees Celsius. And at the time when both the quarter and the beer are at 4 degrees Celsius, well, your heat transfer process stopped. Same temperature, no heat transfer. We will pick up from here on our next lecture.